Okay, welcome everyone to another meetup of the San Diego chapter of Papers We Love. We have a special presentation this evening. One of our co-organizers is going to present a paper which she is the principal author of. Usually we don't have papers which are presented by principal authors, they're just presented by people who are interested. This time we're fortunate to have this paper, and in fact this paper is an award-winning paper. Last month we found out that the ACM, Special Interest Group for Computer Science Education, which runs a conference which has gone for the last 50 years, they awarded the top 20 papers of the last 50 years, and this paper was #1. So congratulations, Lisa, on that honor, and to your co-authors as well. So the paper itself is going to be Identifying Student Misconceptions of Programming by Lisa Kaczmarczyk, Elizabeth Petrick, J. Philip East, and Geoffrey Herman. So let's please have a warm round of applause for Lisa Kaczmarczyk.
Thank you. Hi. Well, this is actually a really nice opportunity because I get to revisit this project with you all, and I love doing this in a small, intimate audience. So what I'm going to do is tell you about this paper. I'm going to talk about the paper, but I'm also going to give you the bigger context because this paper was part of a larger project. And this paper specifically was what won the award, but having an understanding of what the entire context that the paper was part of, I think is important in terms of understanding what the paper is all about, why it got a lot of attention, etc. So that's why it says presented with updates and annotations. So the first thing is I want to share just a little bit of data. Some of you may be familiar with this type of data, and some of you may not. This is showing the bachelor's degrees, the trends of bachelor's degrees in science and engineering from 2000 to 2015. And the computer science is the one that is red with little triangles that goes across the bottom. And what's interesting is this when you compare this to the other subjects. So above it is the social sciences, the biological sciences, psychology, even engineering has more people that have been majoring in it. So you can see that not very many people major in computer science compared to a lot of these other subjects. And it hasn't changed very much over time. Even as we've gone through various periods of, economic boom around, computer science issues and, the economy, it hasn't changed that much. And focusing in on women is also very interesting because it shows you this is women who major in computer science compared to all of the physical sciences, which includes engineering, law school, medical school. And you see that the percentages of women in computer science, the red line, compared to these others, is not only lower, but all of these other fields have been going up. And this goes all the way back to before 1970. So what this is showing you is that, the number of women who are going to medical school, law school, majoring in the physical sciences has pretty much gone up over time, whereas the peak for computer science for women was about 1984, and it's been going down ever since. So if you put these two graphs together, the fact that not very many people have been majoring in computer science compared to most of those other fields that we looked at, science and engineering, and then within computer science, the percentage of women has been going down. And if we looked at a graph for other underrepresented groups like Black, African Americans, Latinos, it would be even more abysmal. This shows you that we have a problem with people in the field and we have a problem with diversity in the field. It's really important because recruiting and retaining diverse, successful computer science students is very important for a whole bunch of reasons. And if we just look at it from an economic perspective here, these are some statistics that were put out by the Bureau of Labor Statistics. These are from 2012, and there are some slightly more recent stats, but they're not much better. So one of the things they projected was that by next year, 1 out of every 2 jobs in STEM is going to be in computing. That shows you how ubiquitous computer science is becoming. And so there's some more stats that just sort of shows you how dominant computer science and the need for people with a computer science background is and is going to be. And notice in parentheses, engineering is far behind. Computer science, 62% of new STEM jobs created through 2020 will be in computing. That doesn't include engineering. When we separate engineering out from computer science, engineering's far behind. So the jobs are in computer science, and they're going to be in computer science. And then you have some of those stats that I was talking about showing you, when it comes to diversity, it's pretty poor. CS1, which is an acronym that refers to the introductory computer science course, is the gateway to studying computer science. And it's hard. This has been hard for as long as computer science education has been around. It's always particularly hard for a lot of reasons, that some of them are very unique to computer science per se. There's a lot of preconceived notions out there that people have about what computer science is, and they're very often wrong. Computer science isn't web development. A lot of people think, oh, computer scientists, they do web development. If you're going to study computer science, that's what you're going to learn. Or you're going to study IT. There's sort of this classic joke that many of you have sort of heard, you walk into a room and somebody says, will you fix my printer? That's not what computer scientists are trained to do when they, get a bachelor's degree in computer science. There's also a very common misperception out there, people coming into computer science, into their first class, that computer science means coding, okay? And that computer science 1, the intro course, is coding. Well, these things are not. The computer science is not coding. Coding is actually a tool. It's a tool that you learn in your very first computer science class and classes that you get a level of mastery of initially so that you can start studying all these other topics that are actually what the heart of computer science is all about. So even in your introductory course, you're not just learning how to code. Yeah, you're learning how to program in some language, but you're already starting to learn about other topics, such as algorithms and databases, and you move very rapidly into, issues of efficiency, computer architecture, you move along, AI, automata theory. These are all the things that you study as you move through your degree, and they assume a mastery of coding so that you can use it to study these other things. And that's something a lot of people don't recognize and they don't know when they consider the field when they start their first course. So, and unlike physics, chemistry, biology, most students coming into their first computer science course have not had any exposure prior. Because even now, even though there's been a big push for the last 5-6 years, the vast majority of high schools don't have computer science as an option. Yes?
Sorry, my first time here, so you said you welcome discussion, I guess?
Absolutely.
Because my question to you is, does it need to be that hard, right? So basically, we've been in this field for 20 years, I can guarantee you, I've never programmed an operating system. I have never used automata theory, like maybe once or twice. I used the big O notation, and I was just, does it need to be that hard?
So I'm going to repeat the question because I'm guessing that it doesn't get picked up by the mic for the broadcast. And so the question from the audience was, does it have to be that hard? And I forgot what your name is. DJ was saying, I've never done those things. Well, what we're talking about here is if you go for a bachelor's degree in computer science, these are the things that you're going to study. There are clearly other ways to work in the field, but if you choose to go through a university degree, those are the topics you're going to be studying. Now, the question of does it need to be hard is a really good question. It is hard. Does it need to be hard? It's perceived as being a whole lot harder than many other fields. And that starts to get at the heart of what we're actually talking about here and what this focus is some of the difficulties that students have studying computer science. Some of the misperceptions that students have coming in because they haven't had any exposure to computer science adds to some of their initial barriers and their difficulties when they start that first course, because most students coming out of high school, they have some idea of what physics is and what physics is for. They have some ideas about what biology is for, chemistry. They have some notion, but with computer science, they usually have none. Or if they do, it's way, way off, as we were talking about a minute ago. And then you add to that, if you're looking at it from a pedagogical, meaning, a teaching and learning perspective, it's very hard to remember what it's like to be a novice. It's very hard for those of us who have a lot of experience, who've been in the field for a long time, whether or not you're an educator, it's very hard to remember what was it like when you first started looking at this material. And so this, has anybody seen this before? So everyone in this room has some experience and some exposure to computer science. They have some exposure to coding. So you have some ideas of how to look at this and to start thinking about what it might mean. And as a couple of people pointed out, one person said it looks like an assembly language, another person said maybe it doesn't look like an assembly language. We bring what we know to what we see when we see something that's new. And I purposely went after something that I figured most of you would probably never have seen. This is actually assembly code for the IBM 360. And this goes back to the early 70s. The IBM 360 was one of the most revolutionary architectures and systems in the history of computer science. And this is from a book, John Donovan's systems programming book from 1972. This is the code for doing a binary search. And this is a book that was for a while used in many introductory computer science classes. It covers a whole slew of topics, and it's all in assembler, because at that period in time, that's what a lot of people were coding in, especially on, the IBM 360, which was, ubiquitous and innovative, and, everybody was trying to get in on that. So you might have had just a little bit of an inkling of what it was like to come at something that you've never seen before. But if you can try to imagine what it'd be like if you had no background whatsoever in computer science and no background in coding, and someone threw that at you, it's like, whoa, okay? But even so, it's very hard to remember what it was like when even that, you would have no idea how to start looking at it. Now, everybody brings, as we were just saying, brings to something new preconceived notions, assumptions, conceptions. They may be right, they may be wrong. But there used to be this theory in the learning community that people were what they called a tabula rasa, which meant that you came to new material like a clean slate. That's sort of the slang for tabula rasa is a clean slate. The idea that you don't bring any conceptions to something new, which would mean that, it would be really easy to teach something new that you've never seen before. In fact, it's great if you've never seen it, because all we have to do is tell you what it is. We tell you what it is, we explain it to you, we show you how it works, we show you what to do. You're going to suck it up like a sponge because there's nothing else there in the way. It should be easy. Well, we figured out pretty fast. Well, actually, I won't say fast. It took a long time. You had to use the psychology research to actually convince a lot of people that that's simply not true. That's not the way people are, and that's not how they learn. We've evolutionarily developed to be pattern matchers so that it's in our benefit when we see something new to try to connect it to something we already know. And if we don't immediately know what we're looking at, we go searching for it in our head. We try to figure out there must be some way that I can connect this to something I know. That's a survival strategy. So when a student looks at some new code that they've never seen, or a programming language that they've never seen, something in CS1 that comes up, they immediately look to how can I relate this to something that I already understand. And this happens at a subconscious level. It's not something that they're consciously thinking about, okay, how can I figure out what this relates to? It just happens. This is the way our mind works. And so particularly difficult for computer science because it's made up of a lot of abstractions, and you hit these abstractions from day one. And when you try to connect them to something in your real world experience, it sometimes pushes you off in the wrong direction, especially when some of the terminology seems to be similar. So array versus array, capital A array is array in computer science. Array is, with a small a, is array outside the world of computer science. They're not the same thing. An object in computer science is not really anything like an object in the world of physical object. And float versus float. Computer science is full of these things. And so this makes it particularly difficult because there's not a lot that's concrete that students can, wrap their minds around when they first come to this. And so misconceptions has been a topic of discussion within the computer science education community forever, going all the way back. There's been lots of talk about it. And there had been, prior to this paper, there had been, quite a bit of discussion about misconceptions. a lot of it focused on what are the mental models that people develop about various topics, you know, what kind of cognitive representations do people create about things, which is kind of like a first cousin to studying actual misconceptions within computer science. And on top of that, a lot of the work was anecdotal, meaning it wasn't approached from a scientific perspective of let's do research, let's not assume what's going on, let's not draw conclusions just by watching a few students or talking about, you know, my experience in the classroom, I've seen a lot of X, therefore it must be true. There hadn't been a lot of studies that actually said, let's look at this, you know, in a scientifically rigorous way and start seeing what we can understand about student perceptions, conceptions in computer science in a way that would then lead to how can we try and educate more effectively. And a lot of the theoretical work wasn't followed up, you know, with actual pedagogical application. There would be theories of this is how, you know, people are thinking or perceiving, but then the next step wasn't taken. So that's kind of where we were before this work. Now there was this idea that was already out there, which spurred the work that led to this paper, called, there's a concept inventory. The original concept inventory was created in physics education. And this revolutionized physics education. It was like, it changed the way they teach introductory physics, primarily at the college level. Although in some cases, you know, depending on what levels of physics were taught, this also changed, you know, the high school level, but primarily we're talking university level. A concept inventory is a multiple choice exam. It determines, and I don't like the word exam, but there isn't a better word. You could say survey, but it's not really a survey either. It's a series of questions to determine whether students are correctly understanding the critical concepts of Newtonian force in introductory physics. Newtonian force was something that for a long time had been known to be particularly difficult for introductory physics students. They just had a really hard time wrapping their head around it. And so it was a big challenge for physics instructors to try to get at what's going on with students and how can we help them to grasp these concepts. So these guys, Hestinis and all, in the early 90s, they published this work that they had done, this rigorous work to develop this thing called a concept inventory, which was designed to get in there and test some specific critical components of Newtonian force, not to be comprehensive of all of introductory physics, but to zero in on topics that were known to be hard, really hard for students, and at the same time were really difficult, and find out what their actual misconceptions were. And that then you could then use the information about what kinds of misconceptions were your students having to, on the ground, then alter what you were teaching in the classroom right then and there to try and address them. So it was not intended to be used for grading students. It was not intended to be used for judging whether faculty were doing a good job or not. It was really intended to be a tool to try and help to get into, you know, the heads of the students that were in the introductory physics class on these specific topics so you could then work with it. And because the concepts that were part of Newtonian force were universally agreed upon, this could scale. It could be used in introductory physics courses anywhere. And so it took off like wildfire. And as I said, it changed the way introductory physics was taught. Yes?
It's the original concept because it's what they understand before they start?
Oh, it's the original concept inventory, meaning it was the first concept inventory that was ever created.
It looks like they would do it at the beginning of the class or the middle or...
You can do it whenever you want.
Oh, okay.
You can say, I want to give the concept inventory to see what's going on. It could be done at the beginning because you want to say, oh, I wonder what my students are coming into the course with. It could be done in the middle because, all right, we're about to get to that topic, or it could be, gee, you know, we're working on this topic and something's not happening here. I want to get some insight. Because you can't go and interview every single student. You can't ask every student, especially in a huge class. I mean, some of these classes in universities can be hundreds. You can't bring all of the students in and talk to every single one of them individually. That's incredibly labor intensive and kind of impossible to find out what's happening. So you could hand this thing out at whatever point you wanted, have your students take it, look at it, and because it's a multiple choice exam, it's fairly easy to rapidly look at the results and say, okay, this is what's going on in my classroom. These are the misconceptions that are running rampant with my students. Now I can do something to try to specifically target that. So the idea then arose that there should be a concept inventory developed for what we call programming fundamentals. And notice we're not calling it CS1 because, again, it's not meant to be, we're not talking about something comprehensive to the entire course. And program fundamentals because the idea is to look at something that is as universal as possible to beginning programming. So along with some colleagues, we got a grant from the National Science Foundation to develop concept inventories for 3 topics, actually. One of them was programming fundamentals. One of them was for digital logic, and the other one was for discrete math. And so there were two universities. At the time, I was at Rose-Hulman Institute of Technology, which is an engineering school in Indiana, and my colleagues were at the University of Illinois, Urbana-Champaign. So PI is principal investigator. Those are the people like in charge of different aspects of a grant. And so I was the PI for the programming fundamentals, and then there were 2 separate people who were the PIs at Urbana-Champaign for discrete math and for digital logic, but we were all working together. The idea was that we would, help each other out and develop these things, more or less in parallel. In the middle of it, I moved to UC San Diego, and so then that's why my affiliation that's on this paper was for UC San Diego, because that's where I was at the time. I'm not anymore, but that's where I was when this work was done. And partway through, I brought in someone I knew from the University of Northern Iowa to help out, and so that's why somebody with their name is also on this paper. So prior to this paper came in the middle of the process of creating this concept inventory. So there was a bunch of work that took place prior to this paper, and you don't need to know it in order to read this paper, but in terms of the big picture of what's this whole thing about, I thought it would be interesting and useful to tell you what happened that led up to this work. It also explains some things about why we did what we did in the paper. But we ran what's called a Delphi process, and a Delphi process is a formal study in which you bring together some experts in some content area, and you use this procedure for collecting information to reach consensus about some topic. And it's structured in such a way to avoid situations where you have any one person or persons dominating the conversation, and to also avoid, say, all right, we're just going to average everybody's. These are the kinds of mistakes that you can get into when you bring a bunch of people in a room that can really lead towards skewed results. If you have people who have strong egos or strong opinions, or a variety of other factors, it can really lead to information that's really biased. So a Delphi process, there's all sorts of, again, it's a process you can read. There's research papers on how it's developed. They're all cited in this paper if you really want to know how does a Delphi process actually work. But as it says in the 3rd bullet point, you use it for situations where you recognize that expert judgment is necessary in order to draw conclusions about some topic when you don't have full scientific knowledge to go and just say, let's go find out, let's look it up, let's find out what the truth is. Okay, so we pulled together a group of pedagogical experts in CS1. We went through this process. It takes months to do a Delphi process properly the way we did it, and to converge upon what were the topics, the programming fundamentals topics that were considered important, really important topics, things students really needed to understand, and difficult. And these things are not always the same. So important topics may or may not be difficult. Difficult topics may or may not be important. The idea here was to converge upon a set of topics in introductory computer science that were both. And so at the end of this process, we had 32 concepts that the group sort of, honed in on that were considered both important and difficult for novice students. So then the next stage, and this is where this particular paper comes in, was to investigate those concepts that the Delphi experts had come up with. And there was 2 reasons for doing this. One of them was to find out, okay, what are the misconceptions that students hold about these topics? The Delphi experts have converged upon these are hard. These are really hard. Students have a lot of misconceptions about these things. Well, we now want to find out what are they exactly. You know, what are the common misconceptions in these areas? And then also, we just wanted to validate the fact that were the Delphi experts on target? Were the things that they had identified, are they actually difficult for students? So by doing these interviews, and these are following a fairly structured protocol that I'm going to tell you a little bit about here too, we dug into those two things. And so we went and brought in 11 undergraduate students who were either in a CS1 course or had recently completed a CS1 course. These are students from UCSD. We also did some interviews with students outside of UCSD, but the ones here that we're talking about were from there. And we had to go through a process that whenever you do this kind of work, you have to get what's called Institutional Review Board approval. There are federal guidelines for how you do research on human subjects, meaning people. And so you have to submit a very formal protocol that follows a lot of things, that do things like protect privacy, confidentiality, you know, make sure you're not going to cause any harm, whether it's physical or psychological. You have to, you submit a whole bunch of pages of paperwork that follow these guidelines, and eventually you get, boom, stamp of approval, so they know exactly what you're going to do, and it's going to be done properly. And this is all based on, if you go back in time in the 50s and 60s, there were some really horrible research studies that were done, and some of them are quite famous, that abused people very, very badly. Things like, you may have heard of them, they injected people with syphilis even after we had the cure for syphilis, because they wanted to see how the disease would progress. So they injected people with syphilis, and they didn't treat them even though they knew how, because they wanted to see what would happen. And this is, you know, quote unquote, all in the name of science. So there were a whole bunch of studies like that. And so these guidelines were put into place a long time ago to try and prevent, you know, any kind of abuse when you're doing research with humans. And so this applies even to educational research. There's different levels that you go through to get approval depending on, is it medical research, is it educational research, is it blah, 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 blah. But bottom line, we went through all of this to get approved before we did this. We focused on 10 of the concepts because realistically, we couldn't look at all of them all at once. So we picked 10 of them, and I'll show you in a moment what the 10 were that we focused on in the interviews. And we followed a protocol. It's called the Think Aloud protocol. And again, if you get really interested, there's citations for all of these things in here if you want to look up, you know, how do you actually do this. And I'll show you again a little bit about how that works here in a second. And we developed these interviews through going through a couple of rounds of pilot testing the interviews, tweaking them, you know, try them again until we got them honed in so they were, you know, looking at what we wanted them to look at and effectively examining the things that we cared about. So these are the concepts that we initially investigated. These are 10 of the ones from the 32 that were identified by the Delphi experts. And we picked these for a couple of reasons. They ranked very high. You know, all of the concepts that were determined to be both difficult and important, you know, they were sort of on a scale of how difficult and how hard and what's the intersection between those two. These were ones that all were very high near the top. These are areas where they identified lots of students have problems with topics, concepts in these areas. Okay. A little bit more information about how we conducted these interviews. We structured it so that every concept that we involved was asked about in several different ways, coming at it from several different angles, so that we were able to triangulate and not just have, okay, we're gathering data based on one question. So if you're you know, if you're looking at things having to do with, you know, some aspect of memory models, there were probably 2 or 3, you know, questions at a minimum that would focus on that topic. And we did all sorts of things to avoid classic areas of research bias, like, you know, rearranging the order, using subsets. There's a whole bunch of things you can do to make sure that, to the greatest extent possible, you're not being influenced by external factors. We audio taped, we videotaped the recordings, the interviews with students. They lasted about an hour. We presented them with these problems that we had developed, and we asked them to talk through their thinking. And I'm going to show you a problem in a minute so you can see an example of what sort of thing we were asking them. And so they would talk out loud about what they were thinking. They were also encouraged to draw, you know, when it was relevant, or write so that they could demonstrate what they were talking about. And some of the concepts were language independent and they didn't involve coding at all, but they were still, relevant for, programming fundamentals. It's again why we're not necessarily calling it coding. But in those cases where we had to have a language, this was a, big topic of discussion. What do we do about that? Because ideally concept inventory stays the same forever, like the one in physics. Newtonian force is not going to change as far as we know. But this is challenging because introductory computer science is based on using a language, and the language changes with time. Lots of anguish just talking about all this pros and cons. We decided for those questions that had to be language-based, we were going to use Java for, a lot of practical reasons. At the time, it was probably the most widely used language in introductory computer science. The students that we were talking to had been, studying Java. And so we figured we had to have an OOP language because some of the concepts were specific to OOP that seemed to be particularly hard for students. So this is an example of what we gave them. This is one of the real problems. And you can just sort of think about that for a second. If you were shown this and asked to, this is taking a look at memory models. How is information stored in memory? So we asked them to take a look at this, and we asked them to tell us and show us what happens here. What happens in memory when you run through this code? I'll just let you think about it for a second, and then we'll move on. Yeah.
So I think this was, or actually, because both the problems were similar to this paper, and I feel like it is. It's one of those things now that even today, 10 years, or when I was doing it just a few years after the paper, like this kind of stuff is not emphasized today, and I don't really know how this. I don't remember how this is going to be in memory.
If you take an introductory computer science course at a university, you will talk about this. So it's still there. It's still in the curricula. They may be using a different language, but if it's part of what's, moving toward a bachelor's degree, these topics are going to come up in whatever language you're using. And it may come up at different levels of emphasis in that first course, but as you move through your next courses, it will continue to come up, especially as you get into, your operating system courses, your architecture courses, things like that. It's there.
So I would say that it is there, in like an operating systems course, but at least from my experience, this was not emphasized.
It may not have been. Yeah. Typically it is, but again, nobody legislates how your course is going to be taught. So I can't really speak to your course, but yeah. It's considered to be important that you know it. Now, if they didn't cover it, that's another issue in itself. So this is what we did. We ran them through those interviews. We asked them all of those questions. We had the transcripts professionally transcribed. Fortunately, I didn't have to do it. I hired someone to do it. And then we ran through a method based on what's called grounded theory, which, to give you a very, very simple overview of grounded theory, you bring in several independent people, independent researchers who take a look at the same data independently. They go through what's called coding it, to identify key points related to the issues that you're looking for. In this case, it was misconceptions. And misconceptions, like in that example, we were looking for things around memory, or other things happen to crop up. But the three researchers each basically analyze all of the interviews independently until they're satisfied they've caught everything, and then they come together and they compare what they've done. And you go through a process where the things that they do not agree on get thrown out, and you end up only keeping those identified misconceptions that they all agree are there. Okay. And we ended up with, and you code them and you give them little labels, and I'm going to show you an example in the next slide or two. We ended up with 32 different codes, meaning 32 different things that we'd agreed, okay, there's something going on here, it's a misconception, and then we write a definition for everything that you've seen. And of those 32, 25 of them focused on the concepts we were actually looking for, which means we also found some things in addition to what we were looking for, which is always interesting. So you take all the codes and then you look at what are the themes. You know, you sort of say, okay, we've got a bunch of them. How do they group? And then you look for overall themes. And we've got 4 high-level themes here. Things that jumped out that we were seeing over and over again, you know, across students and coming in many different ways. So, you know, the first theme had to do with, you know, underlying memory usage. A whole bunch of misconceptions under that, a whole bunch of misconceptions about, you know, how while loops work, you know, understanding of what an object is, and the fact that many students cannot trace code linearly. And that's a pretty fundamental problem there, but there's all sorts of misconceptions that lead to that happening. It's really interesting, and I've had this happen many times, to have a student come into your office and sit down and you say, okay, explain the code to me. You're having some trouble, explain the code. And they start jumping around all over the place. And you're like, whoa, you know, can't you, you know, you're assuming they'll just go through line by line and explain to you what's going on. And no, they start hopping around all over the place. It's, you know, whoa, why? Well, there's clearly some underlying misconceptions that are leading to that. And so that's what theme number 4 there is all about, is the various misconceptions that manifested through students bouncing around all over the place when they were taking a look at code. Oops. There. This is just pointing out that theme 1 and theme 4 are fairly language independent. You know, this shows up and it's not specific to a language. If you're unable to trace code linearly, it's not going to be different because you're talking about Java or Python or C or assembly language. Whereas 2 and 3, 2 is applicable across a lot of languages, you know, both historical languages as well as languages that are currently being used, and 3 is specific to, you know, OOP languages. So these are 4 high-level, you know, areas, categories, themes where we saw misconceptions in these students. This is an example, this is a subset of what some of the misconceptions were underneath one of those themes to give you an idea of what they look like. So we gave them a label, and the label, you know, relates to, you know, which theme they fell onto, on where we found them. We gave them a name, and then we gave them a definition. And so we have this, you know, big long list of all of these. And so the first 1, 2, 3, 4, 5, you know, have to do specifically with misconceptions related to memory, and the last 2 have to do with primitives. So let's go back to this. This is, yes, Marvin.
Go back one slide, just to the one before that. So the semantics to semantics, student applies real-world semantic understanding of the variable declarations. That seems like a larger problem that you'd wind up with people applying real-world semantics to other areas as well. Is that something, were there other misconceptions that were related to that in other areas?
It shows up particularly when we're talking about memory, and in fact that's one of the couple of the examples that I'm going to show you because they were in the paper. It seems to be brought to the surface very strongly there. It does show up in other ways in other places, but it jumps out there. One of the surprises of this research, and I think I mentioned it many slides further on, is that there were so many misconceptions that popped up when we were taking a look at issues related to memory usage, memory allocation, etc. Yes?
You might have mentioned it, and I missed it, sorry, but were roundabouts, were they in their CS1 course?
First course. They were either in it or had recently finished it, which would mean they were in their second course, or, you know, in some cases, maybe we're not taking the second course at the time.
So like well over 3/4 of the way.
I'm trying to remember what point in the quarter we did it. Yes, it was not near the beginning. It was near the end. It was near the end. So the idea was they should have been through all of the topics we were looking at. And there was an assumption on the part of the instructors that we've covered this. So we did a check. We looked at the syllabus and we talked to the instructors before we went and recruited their students and said, you know, our understanding is that this is material that will have been covered. Is this true? Have you? And they said, yeah. So we proceeded. That's a good question. Yes.
I wasn't quite sure that I understood the first one.
Yeah, I'm about to show you. I think, because this is really interesting and it's kind of fun. So this is the example we looked at earlier, okay, in which we asked students to, give us their understanding of what happens, how, when this code is executed, relative to memory. And this is an example of what one of the students said. Now, what do you see going on here? I'll just give you a second. What do you see what they're saying? Somebody want to volunteer what they see is, and I'll repeat it into the mic so that we can record it for posterity. What's the problem the student's having? Yeah.
I guess so my question was going to be, when somebody sees new library, they think this is a good collection of something, but it doesn't necessarily represent how it's being used here.
So they do, yeah, the statement was that a student sees the library and they assume it's a collection of something. That's true. What they are doing is they're assuming a relationship that does not exist. That there is a library, and because in their mind there's also a list of songs, or an array of songs, depending on how they're interpreting this, the songs must be stored in the library. They were making this connection, library, songs, oh, songs must go in the library. They don't know how, but that's their belief. And so I don't unfortunately have the diagrams to show you, but the diagrams showed, this structure representing spaces in a library, and they put the songs in it. And that's what they believed was happening in memory with this. And it's not here, but they believed that, in this quote, but they also believed that all these other pieces were in there as well, because I saw this relationship. Okay, artists, titles, albums, these are all related to songs. Okay, so those are in, those are part of the songs. In other words, they were piling all this stuff in a structure that is not implied, it's not true, it's not there. So this is an example of they were bringing prior understanding from the real world and making assumptions about what was happening internally in the system because of it. And that leads to all sorts of problems. So here's another one. I'm going to show you a variation on this, because it also shows, an interesting, this is another, similar type of a problem. So you can just take a look at that one for a second. What do you see happening here? What is this? What's going on with this student? And these are different students, by the way. It's not the same student over and over again. Yeah, it's a similar kind of a problem. They're saying, okay, cheese, meat, turkey, ham, roast beef, okay. These things are all related. So obviously they're all going in the meat array. Well, these are not even the same type. There's just no way. But their preconceived notions, their assumptions are such that that's what they believe is going to happen.
Perhaps they're struggling to understand those associations which are explicit versus implicit, or something along those lines.
So the comment was perhaps they are struggling with what's explicit and what's implicit. At this point, they appear not to understand what is actually happening with memory allocation and how that relates to what the type is. So therefore, they don't recognize, A, what's being allocated, when it's being allocated, how much is being allocated, and the fact that when you have separate types, they can't be put in the same place. So there's the interesting thing here from a pedagogy, there's lots of interesting things here, but when you think about it pedagogically, when you recognize that what they're doing, and you only find this out when you listen to them, because otherwise you'd never know this is what was going on. You'd look at this code that was just, if they were then trying to write their own program or debug something, they'd be having masses of problems. And once you start to realize that they're making all sorts of associations and drawing conclusions based on real world information that is not helping them, then you start to get, okay, now I can get some ideas about how perhaps I can address that underlying issue that they're having. Because otherwise, if you just keep saying over and over again, you know, no, it's this, and you're not addressing where the problem is coming from, you're not going to affect it. Yes?
So I think for me it's interesting though, because if you just show someone this code, and you know, if they're a software engineer, they're out in the real world, and they're diving into a code base, and they see, okay, there are meats, and then there's some other meat classes, it would probably be a good assumption to assume, like, this meat is hopefully a subclass of, like, the meats class, so, like, hopefully I can stick that thing in there. And just, in any other situation where it's not asking about how memory is actually being allocated here, pulling in those assumptions, and those assumptions being true, would be a sign that it's probably good code, as opposed to, like, nonsensical code, right?
You make a good point. It's sort of parallel to it's parallel to the focus, which is that when you're looking at novices and they show symptoms of they're just not getting something, trying to figure out where they're not getting something is coming from, because this is not necessarily nonsense code. In fact, there's nothing nonsensical about it. It's just, it could be an excerpt of something else. But if you have students that are having trouble writing what seems to be simple code, or reading simple code, or debugging very simple problems, and you don't recognize that the problem is coming from bringing in real world knowledge and applying it incorrectly, then you're going to have a really hard time at getting at helping them to do whatever they're trying to do correctly.
Could the problem be that they just didn't understand the question of how this is stored in memory?
Well, we were asking them how, you know, to show. I mean, if you look at that diagram, how this information is stored in memory. And so they were doing it all wrong. And so the question is, why are they doing it all wrong? By having them talk out loud about why they were saying it's stored this way, you start to realize that's why they're doing it that way. I mean, clearly they don't understand how it's stored, or they wouldn't, you know, be saying what they're saying. But it's that second level of understanding, you know, why? Where's that coming from?
It seems like it's almost this an abstract semantic sort of association rather than a symbolic understanding.
Mm-hmm. Which gets at one of those labels, you know, semantics and semantics. There.
But I think, like, again, from personal experience, that, like, when they were taking this course, the emphasis of the course would have probably been on these are the objects and these are relationships between the objects, and not as much on this is how this is actually going to be laid out in memory.
Well, actually, this material was covered in class. They did have a significant section on, you know, memory representation. It was covered. As I said, that's part of why we went and checked first with the faculty and said, you know, have you covered these issues? Is this something that you've talked about? And it was like, absolutely. We have, you know, we have a whole section on this in our introductory course. So in theory, they should have understood this according to what the faculty thought. The faculty thought, yes, we talk about memory representation. We talk about, you know, allocation of, you know, memory. And so it's definitely not that this material had not been covered. The belief what it's been covered, but the students, they weren't getting it the way that the faculty would have hoped they had gotten it. Back, front.
I'm feeling a bit of this discomfort, and I kind of wonder if we would have gotten different results with just these variables get allocated top to bottom, draw them, rather than database, pseudocode of what this should be like, which kind of sounds like a design problem to me. Is that what you're getting at? A little bit? I mean, I see you're saying also, oh, maybe you're thinking about subclasses and yeah, implicit relationships, but yeah. It would be interesting to see if there could be a difference.
Ask again. I didn't quite follow what you're saying.
The phrasing of the question to me makes it feel a little bit like
I can partially answer your question because given that this was all designed more than 10 years ago, all I can say is that these were piloted multiple times, coming at them from very different ways to see if they were, you know, targeting the misconceptions as they were laid out by the Delphi experts. At this point, I can't remember enough about the specifics about how we did it, but we followed all I can say is a well-established practice in developing this sort of thing to do it. At this point, I can't tell you what that was anymore. One more, and then I'd like to move on. I think you were next.
Yeah. So with like an answer to this question, were you more looking for like, oh, well, this is stored in the stack and this is stored in the heap with the memory model? Is that kind of what you were looking for with this? Or?
I just wanted to see, I should say, we just wanted to see what was their conception of how memory was allocated as they took a look at this code and they looked at each line. What was their understanding of what was going on? It was that as opposed to, you know, anything one right answer, not right answer. It's what's going on in their head. Let's move on a little bit. This is another interesting statement. This gets at what it is. What does it mean to be a variable? What does it mean to declare a variable? And it's just an interesting statement here. What do you see?
Perhaps confusion of nullness or non-nullness versus abstractly being capable of varying a value?
You wanted to add to that?
I guess, are they not understanding like the difference between like primitives and objects? I guess it's kind of what they were saying.
There's definitely confusion between primitive and objects. This gets a little bit at like what we were talking about over pizza earlier, which is that questions of defaults and when is memory allocated and when are default values set. You know, what happens with primitives, what happens with objects. And of course, this is Java, which as we were discussing over pizza is different from JavaScript. So in the language that they were working in, being very confused in this case about what happens with a primitive. And their language reflects the confusion because what does it mean? It's just being, I don't think any value is created. It's just being declared a variable. What does that mean exactly? There's not a clear understanding of what happens in Java with primitives. What happens, you know, objects aren't the topic of this quote per se, but there's not an understanding of what happens.
Yeah, it seems like they don't understand why you would have to do this. Like, so I feel like if you're learning, like if this was in Python, like you wouldn't even know. Like these things would be completely obscure to you, and that might be like a good thing, that might be a bad thing. But here, like I feel like they didn't understand that, like, oh, like the reason why you have to do this before you can use the lettuce variable is because if the students are going to if the students are going to use this data shortly thereafter, you would like them to have some understanding of what just happened here when they get to whatever comes next. And if they don't have an understanding of what just happened here, or they have a faulty understanding of what just happened here, then whenever they get to whatever comes next, whether it's something they're writing or someone else wrote, you're going to start to see problems pile up. And the symptoms of the problems, you know, would probably show up further down. And this gets at, there was a problem right here in the beginning, you know, when these variables were I'll just say written, because the students didn't understand what happened there, so that when they try to use them later or reference them or whatever it is they're going to do with them, and things aren't working the way they want them to work, you might not know to look back upwards here. And I'm a little conscious of the time, so I want to defer on your question and get through this, and then we can talk lots and back up. This is similar, so I'm not going to spend too much time on it, but I just love this idea that it's a blank turkey. You know, what's a blank turkey? Again, you know, lack of understanding of what actually happened here. You know, what is turkey? I just thought that was kind of, I think that one's kind of cute. Oh, and something I didn't mention, I'll just back up real fast. See this one sauce type here? There were several students who totally ignored that. When I asked them, or not always me doing the interviewing, whoever was doing the interviewing, sometimes it was me, sometimes it was someone else. When we asked them to talk about, you know, each of these, there were several students who simply ignored sauce type entirely. You know, they would talk for 15, 20 minutes about this example and not mention sauce type. And the reason was because it didn't fit with all the others in their mind. You know, sauce wasn't related to cheese and meat and turkey and ham and roast beef and lettuce and tomato. For whatever reason, sauce was in some other mental category, so it doesn't exist. So it wasn't drawn on the paper. It wasn't mentioned in the conversation. It's just like it wasn't even there, which is really interesting because they probably were unaware they were doing that. This was happening at a subconscious level. They probably never even realized that they were just not seeing something. 89 misconceptions. We did in fact confirm that the Delphi experts' choice of difficult concepts were in fact difficult. Pretty much, you know, all of them, the concepts that they identified when we, you know, looked at them did prove to be difficult for a lot of students, for most students. We were, as I mentioned earlier, really surprised at just how many issues there were related to memory models, because memory models, especially at UCSD, were quite heavily covered in the introductory course. A significant chunk of time in that course is actually devoted to memory models. So the instructors would have said, yes, this is basic stuff. We covered it. Students are often unaware they're showing selective attention, like ignoring sauce type, and there were examples where students were talking out loud and saying things that were clearly contradictory, and they don't recognize they're saying things that are contradictory. They assume that there's something wrong with the syntax. If they're saying something and what they're saying about relationships don't seem to work, and they're sort of recognizing there's something wrong, they assume the code has a problem. So this is also interesting from a psychological perspective. This tendency to sort of put it out there and not have an internalization about, you know, maybe there's something wrong with my understanding or my logic. You know, the code must be wrong. It's not making sense. It must be the code. The one area where the Delphi experts really kind of missed the boat was that they had come up with a whole lot of very specific misconceptions related to objects, because objects are in fact notoriously challenging. But what we found out was that the students didn't have those misconceptions about objects because most of them just didn't have any idea of what an object was at all. They hadn't even gotten to the point of they were like stymied with the whole idea of objects. So they couldn't have these specific misconceptions relative to the objects that the Delphi experts thought they had. So when you would ask them about an object, I mean, really interesting things happened. Students would just kind of panic or freeze or stumble or, you know, get really embarrassed and say, I don't know, you know, I don't get it. You know, they look kind of ashamed. So it was really clear that one area where this group of, you know, of instructors in general, I think often don't realize is that if you've got the bar set way up here and you're talking about all these issues and they don't understand something that's required at a base level, of course you're not going to get anywhere with these issues. And object is one of those where it came across loud and clear that a lot of students were stuck much earlier. And so that's, I think, you know, a pretty important thing there. So after the work in which this paper was about, we finished the concept inventory, and to make it sort of short and sweet, what happens is that we used the misconceptions that we found to develop the distractor questions on the survey. And so what that means is the inventory, there are a series of questions that ask them about a concept, and there's a right answer. And then there are a series of wrong answers, and the wrong answers are drawn from the actual misconceptions that the students held, as opposed to, you know, us just making something up. And that's how The physics concept inventory was created in other concept inventories that have subsequently been created in chemistry and various other areas. Distractor questions come from actual misconceptions the students held. So we did finish the concept inventory. We beta tested it, we validated it, and it's being used all over the place. Everywhere. Not everyone, but heavily used. So that's what happened with that. So it was, the work was finished. And as I said, it's been distributed around. People continue to work on misconceptions, you know, diving more into it. This whole issue of language independence is never fully resolved because ideally you would like to create, as I mentioned, a concept inventory like the physics one for force, Newtonian force, and it's done and you can use it forever as long as Newtonian force is being taught. You would love to be able to have a programming fundamentals concept inventory, it's used forever, but languages do change in introductory computing, and also although some of the topics are not language dependent and can stay, there's a certain subset of the questions that would have to be reformulated, you know, in a new language, which again would have to be done based on empirical research and not just, you know, winging it together. We had long discussions about pros and cons of handling that issue. But for a variety of reasons that if you want offline we can talk about, we decided we would have, you know, some language dependence in the inventory. And that comes to the end of the talk. Thank you to all these people, the NSF who paid for the work, my colleagues who were a blast to work with, and you guys for letting me relive this project.